Connor.
Hello, can you hear me?
Yep, I can. That's
Okay,
fine.
awesome. Awesome.
Okay. What do we got tonight? I bet we got some hard related rate problems.
Related rates we will get to.
Oh,
And we might get it we might get it sooner than I expected. I'm struggling on inverse trig equations
okay.
or inverse trig derivatives, I should say.
Okay.
But I'm definitely going to want to the exam is next week, so I'm definitely going to be hitting the tutoring sessions fairly heavy.
Okay.
So we'll related rates is a topic to be discussed. Um, I guess to start with, um, like for example, if I have arctangent, right,
Uh-huh.
I can always infer that if it was just arctangent of x, right, it would be 1 over x squared plus 1, or is it minus 1?
It's plus 1. In other words, if a function is equal to the inverse tangent of x, then y prime is equal to 1 over, I put the 1 in front, and the reason for that is that, well, let's talk about that.
Yeah, let's
Let's
dive
talk
into
about the
that.
main three here, because the main three is sine and cosine. Let's talk about the arc sine. So if it's inverse, do you use arc or do you use the -1 to represent inverse?
Usually I use negative, well, yeah, the -1, or to the -1, I should
Yeah,
say.
and you can call it either arc sine or inverse sine.
Yeah,
Either one.
I write it the way you have it, but I try to say it's arc sine just so that there's no confusion.
Okay. And the reason I wrote the first one like that is because the 1 is in front on this one. And the next most important one is arcsecant. In other words, your three main trig functions, and by that I mean not the cofunctions, but sine, tangent, and secant are your three main ones. And this one actually is 1 over absolute value of x times the square root of x squared minus 1, and I left off the square right there. Okay?
Okay.
So that's the way it works, and you will notice that when you are taking functions that are inverse functions, their derivatives are polynomials. They're not trig functions. That is a polynomial. So when we take the first derivative of arc trig functions, we get polynomials, as opposed to when we take the derivatives of trig functions, we get other trig functions. You know what I'm saying?
Yes. And
Now,
so,
this can be a little bit expanded upon using the chain rule. Let's, well,
hang on. Can you table that real? I just have a quick question.
sure.
Um, so when we when we're looking at, I guess let me ask broadly, because when we went over this in class, the way that she had it, the example that we did, it was apologies, it was the arctangent of x, and so essentially is y equals the arctangent of x, just like as you have it here, and essentially he uh, applied tangent to both sides, so you would effectively cancel out the tangent and arctangent.
No,
No?
what you just have to do is memorize what the derivative of these are.
So she basically did trig work to prove, like, for example, that you would get 1 over 1 plus x squared.
Well, maybe in the proof of it, that's what you do. I've never heard of a student that had to do that. In fact, in my calc book, if I open it to the inside cover, I get the derivatives of all functions. In other words, I get all of the derivatives of your trig functions, all the derivatives of the inverse trig functions, the derivatives of natural log, the derivatives of log. And so this is kind of, you just need to memorize this.
Okay. And
Now,
that's what I'm trying to do.
it can get a little more complicated. First of all, let's cover the other three. In other words, the inverse cotangent, because they're similar enough that if you can remember the top three, then these three follow. And it's typical. It's a minus 1 over 1 plus x squared.
Okay.
And when the function is cosine, the cofunction of sine, or inverse cosine, excuse me, y prime is minus 1 over square roots of 1 minus x squared. Notice that they're exactly the same. The only difference is they're minus. So you just need to memorize the top three.
Yeah.
And you can always get the bottom three. Yeah. And usually you have to apply the chain rule here, because it's not always as simple as just x. Maybe it's the tangent of x squared or something.
I was just going to get to that, yeah.
And that is really not any different. You just apply the chain rule. First of all, you might want to take a picture of what I've put up there.
I did.
If you don't have a table somewhere.
Let me just take a picture of it with all 6 of them on there. I took only 3. But
okay. Let me erase everything but the top left one.
Yeah. And if you want, we can modify it, because I have a question that's just now taking the arctangent with the argument of the 4th root of x.
Yeah, exactly. In other words, it's rare that it's just x. Let's say that it is, let me draw this in a different color, y equal the tan, inverse tan, and I'm going to call it u, where u can be anything. U could be x squared, u could be the square root of x minus 1. It's just u is a function of x. Okay, so it's much like the chain rule in that it's 1 over 1 plus x squared times du dx.
Mm-hmm.
And that is frequently written as just u prime, and the u goes there also. So I don't need this dy or du dx, because it's important that you see that it's not 1 over 1 plus x squared. It's u prime over 1 plus u squared. So if I had something like, what's your problem? The square root of
arctangent of the 4th root of x.
Let's put it like this. The 4th root of x is x to the 1/4. Okay? So u, in this case, is x to the 1/4. Okay? So let's apply this. y equals, and what goes into the numerator is the derivative of x to the fourth, which is 1/4 x to the minus 3/4 all over 1 plus u squared, which is x to the half. In other words, if that right there, and u is x to the 1/4, so I have to square that. Okay?
Okay.
And then you could take this 4 and put it down here if you wanted, as long as I put it in front of both terms. And then I could erase it from the top, and that cleans it up a little bit. You could even put the x to the 3/4 in the bottom as a multiplier of that denominator. And that's basically it. Every kind of inverse trig function that you're going to differentiate, most of it's not going to be this simple. It's going to be more like this, where u is not just x.
Right.
So when you look in my calc book, this is the one that's actually used. Is u prime over 1 plus u squared.
Okay. And so if I expand upon this some, given any arc inverse trig function, assuming it takes an argument, it'll actually be sitting into these y prime formulas, whereby we just plug and play for the number.
Yes. Yes.
Okay. Okay. I think that's really it for that. I had there's one problem that was throwing me off on, if I can get to it real quickly, it's logging out of everything. So I have an equation. This is an inverse of just a regular equation. So it's y or f of x equals x plus x to the fifth. Now it wants me
X
to take
plus x to the fifth?
That's right.
Okay.
So now it wants to take the inverse prime of t of that.
Like this?
No, well, just so there's no sign to this. I'm sorry. The inverse prime of x plus x to the fifth.
I'm not understanding the word you're using. It sounds like prime?
Yes. I mean, so it has f to the -1, right? So we're taking the inverse of that equation. So it wants the prime of that, and we're plugging in 2 for that number. So that first half is throwing me off here.
Yeah, hold on a second. I'm not familiar with that terminology, the prime. So you're saying f inverse of x is equal to this?
Well, hang on. It's f of x is just that equation that you have there. So just regular f of x. So if you took the inverse of that, and then you had its derivative,
Okay.
they want to plug in 2 for the x values at that point.
Okay. I think I get what you're saying. First of all, let's see if we can figure out what the inverse of this function is.
Yeah, that's a good place to start.
And the best way to do that is to call it y, not f of x.
Mm-hmm.
And now switch the variables.
Mm-hmm.
And now solve for y, which is not very doable.
Yeah, okay.
In other words, I can do y times 1 plus y to the fourth. but I still can't solve for y. Sometimes when these are quadratics, there's kind of a neat little trick you can use to solve for y.
I was gonna say, if you give me a second, I found the answer online, but that's that's half the battle. I'm just trying to understand how you do this. So bear with me here.
So I'm thinking the next step would be to take the inverse of both sides, maybe. I don't think this factoring helps at all. Yeah, I'm not sure what they're wanting you to do at this point.
So the answer ends up somehow being 1/6. That's the correct answer.
Okay, well, what's the entire problem? This is the function,
That's the
and
function.
then what's the question? Because you were saying something at certain points.
Right. So it's, I guess, so what you have is the original function, okay? So the first part of the question asks to find f of 1. Well, that's simple. You just plug in for x for 1 and you'll get 2. And then you do f prime of 1, or the derivative of that function, and then plug in for 1, and that will give you 6. And then you take the inverse of that function and plug in for 2.
Okay, hold on. Let me not. Here, let's just write some of this down here. So they want to know f of 1, which is equal to 2. And they want to know f prime of 1. So f prime. Ah, that's the prime you meant.
That's the prime, yeah.
Okay. So f prime is 1 plus 5x to the 4th.
Right.
So f prime of 1 is 6.
Right.
And now what?
So now working back with the original equation, but we're inversing it and plugging in for 2.
Let me think about that for a second. So when I tried to solve for the inverse, I got this. And usually you can plug the values. In other words, if f of 1 equals 2, then f inverse of 2 equals 1.
Okay. That makes sense.
Okay. Now, and f inverse of 6, so let's write this. From this statement, we know that f inverse of 2 has to equal 1. And
Okay.
from this, we know that, hold on, yeah, f, oh wow.
So that would be 1/6 then, because if f inverse of 2 was 1, and
I've never seen this notation, where f inverse the derivative, well, let's write it like this. The derivative of f inverse of 6 equals 1. No, that's not right. F inverse of 6 equals 1. And so not sure what the rest of the question is. I mean, we can figure this out. And now, what do they want?
So now I'm following your logic now. So
Okay.
I'm with you now, because if you have if you have f prime of or if you have f1 which equals 2, the inverse of that means it equals 1. And so what they're saying is we're like, where you have f inverse of 6,
Yeah.
if you modified that slightly to, so just parentheses around the f inverse
I
section, we
didn't.
would.
Actually, I didn't do it here. I need to take the. Yeah, this is the inverse. That's the derivative. So it is the derivative.
It is the derivative.
Yeah.
Basically, the
How's
way that
that written when you have the derivative? Would you put it like this?
just put parentheses around the f. The f. I guess there's probably multiple ways of technically notating it, but yeah, you're taking the
Okay.
prime of that when it's 2. So the inverse prime of 2, and that ends up being 1/6 somehow.
The inverse prime, the derivative of the inverse. Let's see. Let's write. Okay. So this is. Um, hold on a second. Um, I don't suppose you have an example that they give you to illustrate what they're getting at here.
Hang on. I just realized I'm gonna drop the way this looks in the chat, because
Okay.
that'll be easier to show. So f, this would be -1. So I don't know if you can see that, but the way that that's written in the chat, it's f raised to the -1, and then there's a little, uh, you know, what
Okay.
would you call that, apostrophe, to represent prime
Yeah, I just got to
of
figure out how
2.
to. Okay, here's the chat. Okay. See if I can open this file.
I just typed it in the chat. There shouldn't be anything to.
Oh, and that little arrow means.
It's a caret to be raising it to the negative first power, if you will, or the inverse of f.
Wow, that's another. Okay, I think I get it now. Yeah, let me move this out of the way for a second. So the question is, let's take that out of there for the moment. They want the f inverse prime of 2.
And the correct answer is 1/6.
Hmm. How would they be getting that?
And it's somehow they're combining. So
Yeah, no,
if we looked at.
I see that we're going to get 1/6 if we put that over that.
Right,
So the
right.
question is why is that the case? F inverse of 2. No. Okay, I think we have to go to this somehow up here. So if that represents the inverse of the function, and we were to differentiate that, we would get, if I differentiate both sides with respect to x, then I get 1 equals y prime plus 5y to the 4th dy dx. So that dy dx is equal to 1 over that. Yeah, actually this isn't quite right. That is what it is. It is 1. It's 1y prime plus 5y to the 4th y prime. And then I factor out the y prime. So, that means that with regards to the inverse, dy dx is equal to 1 over 1 plus 5y to the 4th, and 1y is 1. You get 1/6.
Okay. Okay.
But y is y1, I guess, because of that right there. But I'm pretty sure that this is what's going on. In other words, we weren't able to solve this inverse for y. But we still can use implicit differentiation to figure out what dy dx is. And so I implicitly differentiated both sides, and that produces a 1 on the left side. And when I differentiate that, I get 1 dy dx, and when I differentiate that, I get 5y to the 4th dy dx, which is this. And then I can actually solve for dy dx. It's equal to that. And this y is the inverse. In other words, this is, if I erase this and write it as f inverse, boy, it's weird notation, isn't it?
Well, no, hang on.
Let me write it like, I know how to write this, I just realized. It's f inverse of x prime.
Right, yeah.
And that, they are substituting 2 for x. And we know that when x is 2,
y is 1.
Y is 1 from that right there. Because, yeah, when you look at the inverse of a function, you can just swap the x and y variables. And so when I put in a 2 there, I'm going to put in a 1 there. And that's how you get 1/6.
Okay.
Okay. I don't feel like I explained that all that well, but it is kind of something about inverses that's worth knowing. That you kind of have to infer that when you're talking about an inverse function, you swap the variables. In other words, if f of 1 equals 2, f inverse of 2 equals 1 by definition. In other words, the line I have connecting those two right there, that's the logic you need to use.
Right. Right. Okay. Okay.
And this is the inverse of the original function. So if I'm talking about the derivative, I guess. Yeah. Okay. Yeah, I'm not sure what else to say on this. Um,
We'll leave it there for now.
okay.
That's probably good enough. I don't want to. I wanted to devote some time to it. It's not worth taking up the whole hour. It's just it. As you noted, it's very weird. It's
Yeah.
very weird the way the notation is. And when I was trying to take the inverse of it, I couldn't because you would have two y's there, and it didn't make a lot of
Right. And
sense.
that's the point of this problem, actually, is that you can't actually solve for the inverse. The thing is that you can still come to conclusions about the inverse, such as the inverse of 2 has to be 1. We know that for a fact.
Right.
Now, and that is the inverse, and I can implicitly differentiate that. So I can actually get down to this step right there. Okay.
Okay.
The question now is the derivative of the inverse of 2. Yeah, that's when y equal 1. Now it kind of makes sense to me. Yeah, that's
Yeah.
why it's 1/6. Because you have to go back, and before you differentiated, you know that when x is 2, y is 1.
1.
So you can directly substitute here and figure out uh, this last step, when x equal 2, y equal 1.
Okay. I took a picture of this, so I can always refer
Okay,
back to
and
this.
I am recording this if it helps,
Okay.
and I'll upload it to the same place that I usually upload these to. If you don't have that link anymore, I'll
No, when you say the same place, it's the YouTube channel, right?
yes, on the
Yeah.
YouTube channel. Yeah, or you can
Okay.
just go to the YouTube channel Digital Math Tutor
Okay. Awesome. Awesome. Awesome.
and find it. Your file is always Connor M with the date following it.
Nice. Okay. All right. Let's switch gears then, and actually, I was getting tutoring help earlier on um, uh, related rates. So I guess let's go ahead and do a problem with one of these then.
Okay.
Um, to be frank, the process and the math isn't so bad for me. It's obviously setting up and understanding the problem. That's where it gets really hairy. But anyway, so it says an aircraft is flying at 450 feet or 460 feet a second
Okay.
with an elevation of 135 feet from the ground on a straight line path that'll take it directly over an anti-aircraft gun. How fast in radians per second will the gun have to turn to accurately track the aircraft when the plane is 1,000 feet away, or that's the first part, is 1,000 feet away and then 100 feet away.
Mm-hmm. All right. This is a fairly common related rate problem, but I haven't seen one that asks for the answer in radians. So let me first of all draw a picture to make sure that I've got this correct. I'm going to have the plane going in that direction right there. And it's at a height of how much?
180 or 135 feet from the ground.
And its speed is
460 feet per second.
460 feet per second.
That's right. ST over S.
Okay. And then what else is going on here? Give me more.
The aircraft is flying at that speed, at that from that elevation from the ground. It's on a straight line path that'll take it directly over a anti-aircraft gun.
Okay, so here's the gun right here. Right?
Okay.
And what else?
So it says how fast in radians per second will the gun have to turn to accurately track the aircraft when the plane is 1,000 feet away? That's the first part. The
When the
second part just
plane is
changes
a
the distance.
1,000 feet from this spot here.
I'm assuming so because it's broken into two spot or
Yeah.
two parts. In part A,
No,
it's just
I
asking for when it's 1,000 feet away, and part B is just asking for when it's 100 feet away.
Okay. Okay. So here's our. Let me think about this for a second. If we draw a picture here, I want my vertical line to go like that, and I want that to be the gun is tracking the aircraft when it's above this point over here, and this is theta. So, yeah, I think we can do. I think I can do this, but it's not the easiest one to begin with. There are some really good, easy ones that illustrate the principle of related rates, but I think we can solve this. Because what is theta? Theta is the or the tangent of theta equals 135 over 1,000. Let's call this x. Let's call that y. And let me think for a second here. It's 135 over x. So that is true wherever the plane is. In other words, when the plane is right here, the tangent of theta is 135 over x, however far the gun is from this location. Okay? And y is not a variable. Y is always 135. Whereas x is a variable. So if I let theta equal the inverse tan, I think this is going to be the way to do it, of 135 over x. And now I differentiate both sides with respect to theta.
Yeah.
D theta dt equals, and I'm going to differentiate this with respect to x, and so that goes in my numerator, that's u, 135 over x, and my denominator is 1 plus that squared. 135 squared over x squared.
All right. Just a quick question here, Mr. Tan. I see where your head's at. I guess well, mostly. Why were you working with the arctangent at this point?
Well, um, yeah, hold on one second here. Times d, um,
This is only
times d of
solving for theta.
the derivative of this over x with respect to x. In other words, if this is u, then this is u prime. Let me just write it like that. Might be easier to understand. So this is u prime, multiplying the numerator. And what do we know? We know that the plane, which is dx, God, I hate these ones that use theta instead of time. They're just hard to understand, and that's why I thought it was going to probably be inverse tan problem.
Okay.
Let me think for a second. And they want it at various distances of x, right?
That's right.
And
So
one of the distances is 100 and the other distance is 1,000?
yes.
Okay.
So if I look back at your inverse trig identity,
Let's erase that for the moment. That 1,000 isn't, that's just one of the values. In other words, that is, let's see. If we try to think about this problem, let's put that at 100 feet, starting from here, and let's put that at 1,000 feet. So when the plane is right there, I'm assuming this is their meaning, how fast is the gun turret turning? Correct?
Correct. Or how fast is it?
So that is d theta dt. And the question is how do we, the speed of the airplane is dx dt. Aha, and that's going to be right there. And that is equal to 460. So, let's see, this right here, we can figure that out. That is 130, negative 135 over x squared, right? That's du, or that's du dt. No,
Okay.
that's du dx.
I think it would just be we're gonna be multiplying by u, which would be our dx. Right?
You know, we're trying to solve for that. And our answer will be in radians, I think. Yeah, now the question here, I think we're close here. I just got to think about this for a second. Yeah, let's make sure we get this right. Let me do that again. I'm not comfortable with my... Here, let me just write this again. First of all, let's find out what u prime is. If that is u, then u prime is, here, let me erase some of this stuff. U prime is, let's see, that's 135x to the minus 1, so it's minus 135
over x
minus 2, which is that. Okay?
Okay.
So, now, if I want to know what the derivative of that right side is with respect to time, then I'm going to take both sides with respect to time. Okay, so that puts u prime in the numerator, minus 135 over x squared. And what goes in the denominator is 1 plus u squared, which is actually 135 squared over x to the fourth. And now, wow, we also know that dx dt is that. Do I need a dx dt in this thing? I think I do. Yeah. I need a dx dt. Where's that going to go? In other words, if it was there, now we could solve it. Because I would substitute 460 for that, and I would substitute 100 for x, and I would substitute 100 for this x, and I'd get a d theta dt. And then to figure out what the rate d theta dt is when x is 1,000, I would do the same thing.
Why were you plugging in for x? Okay, so hang on, let's see.
The question is, how did that dx dt get there? When I differentiated both sides, I am left with a du dt, which is minus 135 over x squared, must be dx dt, next to it. Do you have an answer on this one? Because I can check and see if this is correct.
I was going to try to type this in real quickly. Yeah, I was going to see if this would work.
In other words, if this is correct, down here on the lower left, then d theta dt, when x equals 100, is going to be minus 135 over 100 squared.
Oh, okay.
Times dx dt, which is 460, all over, yeah, the sign on these is the 460, because it's going to the left, is actually a minus 460. So let's put that in there. All over 1 plus 135 squared all over 100 to the fourth, which is this with 8 zeros. In other words, it's that number squared. And that would give you a number. The question is that in radians?
So that's coming out to be like 6.198 something.
Okay. And you
Let me see.
don't have the answer to this one anywhere?
I mean, I can Google it. This was doing X as 100. Is that right?
Yes.
Okay. 6.197.
You can actually Google this problem?
Everything is on the internet, Mr. Cohen.
Really? A related,
Oh, yes.
how do you define it as a related rate problem and the positions of everything? And
Because thankfully the school curriculum is taught nationally, and so this problem is, in fact, this software is used as the Mathematical Association of America. So this is, I bet you, a typical problem. Let's see. Okay, this isn't quite the same, but it's nearly the same, and it's close enough for. Hang on, hold on. Yeah. Instead of 135, it's 120. So they're showing flying at 460 per second, or feet per second, an elevation of 120.
oh, not 135?
Yeah, well, no, that's my problem. This is the numbers are different.
Oh, okay. Okay.
So
Okay. I
I'm
see
just
what you're
reading
saying.
through. So they set it up similar. They have tangent of theta equals h over x,
Yeah.
and then it looks like they took the derivative of tangent, which would get you secant squared equals a, a negative h over x. I think that's
So
squared.
they didn't turn it into a theta equals. They took the derivative of both sides.
So let's see. This was
Shall we try it that way and see?
Yeah, let me try this real quickly and make sure I'm not getting ahead of myself because I don't know if this is actually right. I'm just seeing if someone
I
did
think
this.
this may be right though.
100. Oh, I need 135 there.
I don't
So
think it actually will matter because I solved for theta, and they're just taking the derivative and going to put secant squared equals this right there. Um,
and then they're multiplying this by a negative
460.
460. Okay, so let's go back and try this now. So this was for 100.
Let me re let me resolve this.
2.2.
Let me erase just a little bit so I have enough room
Okay,
to write
so
here. If I do it that way, I get secant squared of theta equals minus 135 over x squared. In other
okay,
words,
and that's what
all
they
I
did.
do is I take the derivative of both sides.
That's what they did.
With respect to theta,
Yes.
okay,
D theta over
since x
time.
is not theta, I got to follow that with a dx d theta.
No, well, it's d theta d over dt. It's still with respect to time. Oh, no, no, I'm sorry. No, I'm sorry. You're right. I'm sorry. You're right. You're right. I apologize. I apologize.
Um,
Because then the next step they did was they took the square root of both sides.
okay.
So they get secant theta is equal to the square root of, looks like h squared plus x squared over x. Their handwriting is really bad, but that's what it looks like to me.
Well, I'm not sure what we do about that either. Dx d theta isn't defined, or is it? The speed of the airplane is with respect to time. So this is defined, but I don't know what dx d theta would be.
It would be 460.
Dx d theta is 460? Or
No, no,
460
no, 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 no. I'm
because
sorry.
that's feet per second.
Given that,
So that's got to be that's got to be dx over dt. That's the whole thing about related rate problems is that most of the time is what you're differentiating with respect to.
right?
And these angles just are second degree level harder to understand.
Well, yeah, so secant of theta is equal to the square root of h squared plus x squared all over x, and d theta over d time is equal to negative h over x squared plus h squared times dx dt. So where they have where I changed my numbers, but what the equation ends up working for is negative h over 130 or 100 squared plus 135. So squared. So in my case, I would have negative 135 over 100 squared plus 135 squared times a negative 460. And that got me 2.2. And that was correct in the system, correct in the problem.
Okay.
So dx dt in this case, it looks like is gonna be the flying rate,
Yeah.
the rate at which it's
Um,
flying.
we only have 4 minutes left. Do you mind if I give you a basic related rate problem that
That's
really
probably
will
better.
illustrate
Yeah, that's probably better.
better? There's the falling ladder problem. And this really illustrates it better. You have a ladder that's 10 feet in length. Okay?
Okay.
It's falling at the top. This is the y-axis, this is the x-axis. And the speed, in other words, dy dt, is the speed at which it's falling. And since it's shrinking, it's a negative, and I'm going to call it 2 feet per second. And the model that describes this is x squared plus y squared equals 10 squared. In this case, it's a constant. And now if I differentiate both sides with respect to time, I get 2x dx dt plus 2y dy dt equals 0. And now the question is, so how fast is this end of the ladder moving in this direction when x is equal to 6 feet and y is equal to 8 feet?
So now we can plug in for those values.
Yeah, exactly. We know what dy dt is. It's minus, so let's plug everything in. So we're saying when x is 6 and y is 8. So I'm going to plug in 6 for x, so it's 2 times 6. dx dt is what we're trying to solve for.
Right? Plus
And then everything else, the y is going to be 8. And the dy dt is minus 2. And the sign here is critical, and it's not whether it's going up or down. I was mistaken earlier when I said that. It's whether this is increasing or decreasing. And in this particular description, it's falling, so y is decreasing. So I know that the change in y has to be negative. X, on the other hand, is increasing. So dx dt better come out to be positive. It's moving to the left, but that doesn't mean negative. What's happening is this distance right here is increasing. Okay? And if I solve this, I'm going to take that and put it on the other side. I'm going to divide by 12, and I'm going to have a positive number. So dx dt in this particular case is going to be 32 divided by 12 feet per second. In other words, if that ladder is falling at that speed, what is this speed, the related rate? Because we don't know what that rate is, we have to calculate it, but we can use related rates to do it. And that's the whole point of related rates, is you know one rate, and you're trying to figure out a different rate. And this, one of the hardest things to get on these problems is whether they're plus or minus. And the whole thing needs to be based on, is this decreasing? Is y decreasing? Then it's got to be negative. And is x increasing? Yes, it better come out to be positive. And
Okay.
it does. Okay. And sometimes this is a variable, z, like when I had the car chase with the cops and robbers. And that's actually a real life problem, because if the cop is heading towards the intersection, you know his speed, and he's got a laser pointed at the chase car, or the car that's being chased, and this is real life, they have lasers, he can point it at that, so he knows what dz dt is. And knowing what dy dt is and dz dt, you can figure out what dx dt is going to be.
We can come back to this. So the problems on this software are kind of brutal. Where I really struggle with related rates problems, Mr. Cohen, is actually just in the setup of the problem.
Yeah. Well, that's kind of the basis, is you have to draw the setup and then come up with an equation that applies at a given point in time.
Right. And then from that point, it's easy for me to plug in the numbers.
Yeah, and in this case, z was fixed because the length of the ladder isn't changing. It's always 10 feet.
Mm-hmm.
But in the other case, this is equal to z squared, and you can still do the problem if you know 2 out of the 3 rates. And then you can calculate the third one using related rates. But yeah, to me, this really is related rates 101. This is the first thing you should be taught, is that one. And then maybe related rates 102 would be a police car, where this is a variable. That's now z. And you use the same picture, though, which is a triangle. And you're always going to use either the Pythagorean theorem as your basic equation that fits this picture, or in the previous problem where it was theta, we're going to use a trig function that we know to be true. Since they're talking about an angle that is changing and the speed of that angle, yeah, it's just that's just a harder related rate concept even.
Mm-hmm. Yeah, what we're doing in class is actually working with most of the geometric shapes, actually.
Yeah, I would say most related rate problems are going to end up using the Pythagorean theorem.
No, I mean with regards to like cubes and conical shapes and things like that.
Yep. Well, when you have another really common related rate problem is you have a cone, and yeah, what is this one? This is yeah, where they tell you the rate that the radius of a spherical balloon is increasing, and they'll tell you the change in the volume And they want to know, well, how is the radius changing? So it's not really this problem here. It's if you had a balloon that was being blown up and you know how fast its volume is changing. And the question is, well, how fast is its radius changing? Well, you start out with what is the volume of a sphere? It's 4/3 pi r cubed. And you differentiate both sides with respect to t.
Okay.
So you get a dv dt right there. And over here, you get a 4 pi r squared dr dt. So they're going to give you that, the rate that the balloon's being pumped up, and then they're going to say, what is this when the radius is at this distance? Say, when the radius is 3, what is dr dt? And it's just plugging everything in. But the solution is always to define that first, whatever formula fits the model, and then usually to differentiate both sides with respect to time. And then plug in all the stuff they give you. And usually they'll give you the dv dt because they know that the balloon is, you have 1 cubic meter of air being pumped into it every second. Therefore, dv dt is 1 cubic meter per second. They want to know, well, how fast is its radius? How fast is the radius changing? And the radius changes at a different rate depending on what the radius is. So that's this is a very typical related rate problem.
And like I said, we'll definitely come back to it because I want to make sure I'm really strong on all these.
Yeah, and
past couple topics have been tough.
let me see if I can find one. I've got one here that, wow, this one uses the law of cosines as your basic. I've got one here exactly like the one you had, where
the aircraft one,
tangent of theta, and then they take the derivative of both sides. Yeah. Here, let me just briefly give you this, because this will make sense to you. If I know that this is true, and we had this and that other problem, and now if I take the derivative of both sides, I get the secant squared of theta d theta dt. That's what we didn't do last time. We didn't take d theta dt, or did we? I don't know. But anyway, this becomes 1 over 2000 ds dt.
Okay.
Where S is the S is the height of the rocket. Yeah, this is a similar problem where S is the height of the rocket, and in this particular problem you have a rocket ship going straight up and something is following the trajectory of the rocket, and that's theta. So this is S, and therefore you know the tangent of theta equals S divided by, and this distance here in my problem is 2000, and this is solved exactly the same, and yeah, the answer actually comes out to be in radians per second, oddly enough, because you need to solve for that.
And does it say to square root both sides?
Here's the step that I wasn't calculating, but that's the picture of it. Let me show you the next step. Yeah, but not quite. What they do is divide both sides by secant squared and then convert it to cosine squared, right? In other words, the next step is d theta dt equals that whole right side divided by secant squared, right?
Okay.
Well, when secant squared's in the denominator, it's the same as cosine squared. So it becomes this. And times ds dt. And their ds dt is 100t. Because the basic function was s equals 50t. Yeah, here we go. This was part of the problem. S equals 50 times t squared. And so when ds dt equals 100t. So now I can substitute 100t for that.
Okay.
And then I can figure out d theta dt at a particular time and height, and the answer does come out to be in radians.
So to set up the equation, they have it as cosine squared.
Well, that's the key step in the other one too that I didn't think about. You're not going to take the square root of both sides from this step. What you're going to do is divide both sides by secant squared theta, which turns into cosine squared theta in the numerator over here.
Okay.
Divided by 2000 times ds dt. And ds dt is that. So I can replace that with 100t. And now the question is, what is this when t is hold on one second. Oh, wow, this is really cool. Yeah, you know what you substitute for that?
S was the height, right? So
in other words, the cosine squared of theta is 2000 over the square root of s squared plus 2000 squared.
Yeah.
And that's from knowing the cosine of theta equals 2000. Cosine is adjacent over over hypotenuse. And the hypotenuse is the square root of s squared plus 2000 squared. So it's this step right there that's the tough one.
Yeah.
In other words, that has to be converted to that and then squared.
Oh, okay. Okay. I see.
And squaring it isn't that big of a problem because it eliminates the radical sign from the denominator, makes the 2000 4 million, and everything else goes away, and you end up with that giving you a number. When you substitute, instead of cosine squared of theta, that's cosine of theta based on trig, adjacent over hypotenuse. This is the hypotenuse, that's the adjacent. So it's adjacent over hypotenuse, and And since we need cosine squared, we square this whole thing. And then we can solve at any given time what d theta dt is going to be. Yeah, that's the way you want to do that other problem also. Is go from there to there, and then go to that step, and then figure out what cosine of theta is in your model.
Okay.
From trig. In other words, cosine of theta is always the adjacent side over the hypotenuse. In this particular problem, 2000 is the adjacent side. The hypotenuse is the square root of 2000 squared plus s squared, based on the definition of cosine.
Okay. Okay.
In other words, here's theta, and the height of this thing is, or the distance is that. The height is an unknown because the rocket is flying upwards. And so if I said the cosine of theta is s, where's the 2000? Yeah, it's 2000. Yeah, it's this over, well, what is this? That's the square root of 2000 squared plus s squared.
Mm-hmm.
Just from the Pythagorean theorem. So you know the cosine of theta is is 2000 over that. Cosine squared of theta is that squared over that without the radical sign. Yeah, that's how you do it. And this leap is the hard one, where you have to plug in a polynomial for cosine squared of theta.
Okay.
Yeah.
Like I said, we'll come back to these. This is a big topic. I don't want to.
No, I get it now, actually. So I'm glad I looked in my book and found a similar problem as what you had, where they start out with the basic equation as tangent of theta equals something, and then they differentiate both sides, they get secant squared, and then they divide by secant squared, turn it into cosine squared, and then you have to figure out what cosine is. And just substitute it all along, and you'll come out with the answer. For sure.
Okay.
Okay? And I've kept you long enough. I apologize.
No, it was worth it. I mean, again, we'll probably have to revisit it.
That's fine, but at least I understand it now.
All right, Mr. Cohen. I appreciate the time as always. You have a good one.
Okay, you too. Bye-bye.